All right, let's dive in. Today, we're going to pull back the curtain on one of the coolest tools in machine learning, the decision tree. So how can a simple flowchart, like the ones you'd sketch on a napkin, learn from data to make these super complex predictions? Well, that's exactly what we're here to find out. Let's get into it.
So let's put ourselves in a real-world scenario. Imagine you're a bank, right? You've got thousands of credit card applications piling up. Every single one is a gamble. If you approve the wrong person, you could lose a ton of money. But reject the right person, and you've just lost a valuable customer. This is what we call a classic classification problem, and it is the absolute perfect stage for a decision tree to shine.
Okay, so section 1 is all about making a simple decision. The big question. Can we predict who's creditworthy and who isn't just by looking at the data they give us?
Now, to keep things simple, we're going to zoom in on just two big factors: how much money an applicant makes per year and what their credit score is. The real puzzle here is, can we actually find a hidden pattern in just those two numbers? A pattern that can reliably tell us who's likely to get approved?
And this is where the magic happens. This is where the decision tree steps in. What it does is it takes all that messy data and transforms it into this really logical, super easy to follow flowchart that basically gives us our answer.
So first things first, we've got to try and see the data the way the machine sees it. Just picture a scatter plot, okay? Every single dot on there is one applicant. Where it is on the chart depends on their income and credit score, and its color tells us if they got approved or rejected. And you know what? Almost immediately, you can start to see these little groups, these clusters starting to form.
Now, the algorithm's whole job is to figure out the best way to slice and dice these clusters. It starts by asking really simple questions to split the data. For instance, what if it just draws a line right here and asks, hey, does this person make more than $110,000 a year? Just that one simple question, that one split, instantly creates two much clearer groups of people.
And in decision tree lingo, that very first question, that's our root node. Think of it as the top of the pyramid. It's the starting point that takes everybody, the whole data set, and makes that first, most important split. Okay, so from that root node, the tree starts to grow branches. You've got a yes branch and a no branch. These can lead to even more questions, which we call decision nodes, that keep refining the groups. Or they can lead to the end of the road, a leaf node. And that leaf node, that's the final answer. It tells us point blank, approved or rejected. Okay, now we're getting to the really cool part. How in the world does the tree know which questions to ask and why in that specific order? Well, it all boils down to something called the purity test. I mean, think about it. Why ask about income being over 110K? Why not 100K? Why not ask about the credit score first? See, the algorithm doesn't just guess. It's actually super methodical. It searches for the one split that will create the cleanest, purest groups it possibly can. And the key concept here, the word you need to know, is impurity. An impure group is just a messy mix, right? Some approved, some rejected. A pure group, on the other hand, is one where pretty much everyone has the same result. The algorithm's whole mission is to ask questions that make the groups purer and purer with every split. But, and this is a big but, chasing purity like this can actually cause some problems down the line, as we're about to see. So let's break that down. A node with high impurity might be, say, a 60-40 mix of rejections and approvals. It's kind of fuzzy, right? You're not really sure. But a low impurity node, that's way clearer. Maybe it's 80% approved and only 20% rejected. Making a call there is a whole lot easier. The tree's goal is to create as many of those low impurity, clear-cut nodes as possible. So you might be wondering, how does the algorithm actually measure this impurity stuff? Well, there are two main ways: Gini impurity and entropy. Gini impurity is all about figuring out the odds of messing up if you randomly label someone from the group. It goes from 0, which is totally pure, up to 0.5. Then there's entropy, which is actually a concept borrowed from physics. It measures the randomness, or disorder, in a group, on a scale from 0 to 1. But honestly, at the end of the day, they're both just trying to do the same thing: put a single number on how messy a group is. And here's the kicker. The algorithm literally calculates the impurity for every single possible split it can think of. So, as you can see here, if it splits on annual income greater than $110,000, it gets a Gini score of 0.39. If it splits on credit score greater than 690, it gets 0.40. And because 0.39 is just a tiny bit lower, that means the income split makes the groups just a little bit purer. And boom, that's our winner. So this really lays out the whole game plan, doesn't it? Step 1, test every feature at every possible cutoff point.
Step 2, calculate the impurity score for every single one of those potential splits. Step 3, pick the one with the lowest score. And step 4, you take your 2 new, smaller groups, and you just do it all over again. It keeps repeating this process over and over until it just can't make the groups any pure. But remember how I said chasing purity can cause problems? Well, here it is. This obsession with getting pure nodes can lead to one of the biggest headaches in machine learning: overfitting. And that's basically when a model learns the data you gave it a little too well. See, if you let it, a decision tree will just keep splitting and splitting until every single person from the training data is in their own perfect little box. It's not really learning anymore, it's just memorizing. It memorizes every little detail, including all the random noise and weird outliers. And the result? It looks like an absolute genius on the data it trained on, but the second you show it a new applicant from the real world, it just falls apart. And that right there is the classic definition of overfitting. The model is way too complex and it can't generalize. Now, the opposite of that is underfitting, where the model is just too simple and it's bad at everything. What we're always looking for is that perfect sweet spot right in between those two extremes. So, how do we actually fix this overfitting problem? Well, the solution is actually pretty elegant, and it's called pruning. Yeah, just like a gardener with a tree, we're going to trim back some of the branches to make the whole thing healthier and ultimately more useful. So, what is pruning? It's literally the technique of strategically snipping off branches from the tree. We're getting rid of the bits that aren't really adding much value, the ones that might just be based on random noise. The whole point is to end up with a simpler tree that actually does a better job on data it's never seen before. And there are basically 2 flavors of this. First, you've got pre-pruning. That's where you set the rules before you even start, like telling the tree, hey, don't grow any deeper than 5 levels. You stop the complexity before it gets out of hand. Then there's post-pruning. This is the opposite approach. You let the tree grow as big and wild as it wants, and then you go back and trim away the branches that aren't really pulling their weight. A really popular way to do post-pruning is something called cost-complexity pruning. It's a bit of a mouthful, but the idea is simple. It does the math on a basic trade-off. Is the little bit of accuracy I get from this branch actually worth making the whole model more complex? It basically puts a price on each branch and snips off the ones that just aren't a good deal, leaving you with a much leaner, more robust model. And really, this is the key takeaway. Once you get your head around these 2 core ideas, the constant push to reduce impurity and then the need to prune the tree so it can generalize, well, suddenly decision trees don't seem like some mysterious black box anymore. You can actually follow the path from the first question all the way to the final answer and see exactly why the model made the choice it did. They're super interpretable. Which kind of leaves us with one last thing to think about, right? In a world that just keeps getting more and more complex, the whole story of building a decision tree and then pruning it back reminds us to ask a really important question. When is the simpler answer the smarter one?